And yes, thank you to those of you who have turned on your cameras. It's always appreciated. And if you're still willing to turn on your camera, that's great. I hope lab is going okay. How do you guys feel about the lab? It's this first lab is always it's always the toughest with everything getting set up. You have to do like install tiny tech and try to get things working. And again, I'll have office hours after class today, and so if you have questions or issues, I can help out. I also have office hours tomorrow morning at 10, and so that's available as well. So we're here to help. We don't want these things to be a source of great burden and sadness. Okay. I believe the quiz grades have also been posted from quiz one, quiz grades, and your homework grades have been posted, I believe. So if you believe we made a mistake with either grading the homework or the quiz or something like that, go ahead and submit your regrade requests through Gradescope. So Gradescope has the ability to request a regrade, and you can do that. Also, I'm happy to go over the answers to any questions or anything like that during office hours. So if you got something wrong, you can stick around for office hours this evening, or come tomorrow morning, or whenever. There's no time limit, so you can come next week or whatever and ask about any of your past quizzes as well. And I'm happy to go over the answers there. Okay, well, we'll move on, and we are going to introduce probability distributions. So last week we talked about probability, calculating the probabilities of events, and so we looked at random variables, and now we will specifically look at probability distributions. So a probability distribution basically just describes the probabilities that a random variable can take. And so we saw, some of the most basic ideas of probability distributions when we just had a table of outcomes along with their corresponding probabilities. So we saw that last week when we talked about, spinning the wheel or spinning the arrow on the wheel. And if it lands in this section, you win $0. And if it lands in this section, you win $5. That's the table that has the probability with each of those outcomes is technically a probability distribution. And basically, again, to recap what a random variable is, it's the numeric outcome to some kind of random trial. And what the important thing for a random variable is that the outcome of the random trial has to be a number. It has to be a number. If it's not a number, we can't call it a random variable. So if it's a categorical variable, you've got to find some way to turn it from categories into numbers for it to become a random variable. And then, some of those outcomes are going to be more likely than other. Like when we spin the wheel to win a prize, winning $0 is the most likely outcome. Okay, whereas winning $800 or $5 or whatever is has a low likelihood. Okay, and then the probability distribution shows the probabilities associated with each of those with each of those outcomes. Okay, and we saw them represented with tables last week. We can also represent them with graphs. And so here's just a few examples here. So one example is we can roll a die. Okay, so if you roll the dice, 6-sided die, each side has the numbers 1 through 6, and each side lands with equal probability. And so the random variable is going to be the number that it lands on, and therefore the probability distribution can be represented with this table where each of the numbers 1 through 6 appear, and the probability of each number is 1 out of 6. Okay, and so this shows that each probability is 1 out of 6, and there's no surprise there. Okay, if we want to represent it with a graph, we can represent it like this. We have the outcomes 1, 2, 3, 4, 5, 6, and there is a little line for each one, and the height of each line is 0.1666666, right? The 1 out of 6 is 0.167 or something. And the height of each of these lines is 1/6. Another example is we could flip a coin. And again, a coin flip is generally, the outcome of a coin flip is often considered to be categorical. It either lands heads or it lands tails, okay? But in order for it to be a random variable, the outcome has to be numeric. So what we have to do is we convert it from how did it land, heads or tails, into a question where the answer is pretty much the same, but it's now numeric. So we can just say, how many times did it land heads? How many times did it land heads? And now the answer is going to be it landed heads 1 time, or it landed heads 0 times, okay? And now that we have a numeric answer, and landed heads 0 times or it landed heads 1 time, now it's a random variable, okay? So again, it's sometimes it's as simple as that, as to just say, like, how many times did this happen? And then it becomes numeric, and now you have a random variable. So in this case, landing heads 0 times will happen with probability 0.5. Landing heads 1 time will happen with probability 0.5. Okay, and so this will be the probability distribution for a coin flip and the number of heads we observe after 1 coin flip. Okay, and so this is what the table looks like, or the graph looks like. And this is just the default formatting for a plot here. And so we have a line at 0 with a height of 0.5. We have a line at 1 with a height of 0.5. Okay, so and we can further complicate these things a little bit more, such as saying we're going to flip the coin 2 times. Okay, we flipped the coin 2 times, and when you flip a coin 2 times, the possible outcomes of flipping a coin are going to be heads followed by heads, heads followed by tails, tails followed by heads, and tails followed by tails. Okay, so these are the 4 possible outcomes. And again, we have to have a numeric outcome. So what we can do is we can just say how many heads appears after 2 coin flips. Now, what this will do is it will end up combining some of these outcomes. So if we say how many heads appear after 2 coin flips, okay, we can get the probability of getting 0 heads. That's going to be 1 out of 4. That's going to be tails, tails. This will be 0 heads. And that happens with probability 0.25. Okay. And then we have the probability of getting 1 head. 1 head is heads, tails, or tails, heads. Okay. So we have heads, tails, or tails, heads. And each of those is 0.25. So the total probability is 0.5. Okay. And then finally, what's the probability we get 2 heads after 2 coin flips? And that's going to be heads, probability of heads, heads happens with probability 0.25. Okay. And so we have the outcomes 0, 1, 2, and we can get 0 happens with probability 1/4, 1 happens with probability 1/2, and 2 happens with probability 1/4. Okay. And so those are the outcomes for this random variable of how many times did the coin land heads after 2 flips. Okay. So far, so good. Okay. And then, and when you plot it, now we have bars that are lines that are slightly different heights. We got this line at 0, which has a height of 0.25. This line at 1 has a height of 0.5. And this line at 2 has a height of 0.25. Okay, so that's great. And now we can introduce a specific kind of random variable known as the binomial distribution. And you guys saw this in your homework this past weekend. And so some of you had to kind of, I guess in order to do the homework, you had to kind of learn a little bit here. But we'll cover it more formally here as well. And so we'll go over it. Okay, so binomial distribution is a probability distribution for a special kind of random variable. Okay, and so these are the criteria that must apply or must hold true if we're going to try using the binomial distribution. Okay, so what we're going to do is we're going to repeat the same trial, but we're going to repeat it n times. So whatever whether it's 9 times, 20 times, 3 times, whatever, however many times you repeat it, that's the letter N, okay? And every time you repeat the trial, we're going to just classify it into 2 outcomes. Something happens or it doesn't happen. Okay, we label these outcomes as success or failure. And success we normally associate with being a good thing, and failure we associate with being a bad thing. But this doesn't necessarily have to be an actual good or bad thing. So in some cases, let's say the question is something like, did we detect the disease? Okay, and the question is, the answer is either yes you did or no you didn't. And it's awkward to say, but using the traditional labels, you would say the detection is a success and not detecting would be a failure, although we don't actually want to detect a disease or something like that. We don't actually want people to have an infection. So don't focus too much on whether it's a true success or not. Just think of it as something happens or it doesn't happen, okay? And those are the 2 possible outcomes, okay? So if you're dealing with some kind of categorical variable with multiple outcomes, right? Like we're looking at cars and the color of the car, and a car can be like white or silver or black or red or blue or something like that. You have to turn it into, is the car, is it a red car? And it's going to be, it either is a red car or it's not a red car, okay? And you can't do this for like multiple different colors at the same time. You have to kind of break it up into separate things, and you can have one binomial distribution for, is it a red car, yes or no? And then you have another separate one for, is it a white car, yes or no? Is it a silver car, yes or no? Is it a black car, yes or no? Something like that, okay? Question, how do we categorize the variable as success or no success? The answer to that is it's arbitrary what you call a success or what you call a failure, and the answers will be the same as long as you remain consistent with the other values. So whatever you call a success, that the probability of recording a success has to be is going to be P, okay, and then the variable X is going to be the number of successes, okay? And each trial must be independent of the other trials. So kind of going back to the question, what if you labeled something a success and somebody else labeled the other thing as the success, right? So, let's say you have a bag and you either have red marbles or blue marbles, okay? And let's say it's like 70% red marbles and 30% blue marbles, okay? So you could say, what's the probability, we're gonna draw 5 marbles out of the bag, and you can say, what's the probability I get 3 red marbles? The probability of getting 3 red marbles out of 5 is going to be equal to the probability of getting 2 blue marbles as well, okay? So whether you're looking for the red or whether you're looking for the blue, as long as you're consistent, so the probability of getting 3 red marbles will be the same thing as the probability of getting 2 blue marbles. We'll look at an example, and hopefully this will make a little bit more sense here, okay? So just to kind of make sure we can keep track of everything, we'll look at a coin, and we're going to say this is a special coin where the probability that it lands heads is going to be 0.7, and the probability that it doesn't land heads or that it lands tails is going to be 0.3, right? And so, and what we're going to do is we're going to flip the coin 4 times. And, every time we flip a coin, the coin flips are independent. So, what happened in the previous coin flips isn't going to affect the next coin flip. And so we ask, what's the probability that we get heads exactly 1 time out of 4 flips? Okay, this is going to be a binomial situation, and we can find the answer. We can find the answer using classical probability rules, and we're going to start there first, and then we'll work into getting to the binomial formula here. Okay, so what we do is we say, all right, what are the possible outcomes that could happen when you flip a coin 4 times? And when you flip a coin 4 times, you can get heads followed by 3 tails. You can go tails, heads, tails, tails. So these are all of the possible outcomes that you can get for getting 1 head and 3 tails in 4 flips. Okay, so if you're going to get exactly 1 head, exactly one head means you also have to get exactly 3 tails for a total of 4 flips. Okay, so you're going to get, these are the 4 possible outcomes. There's no other way to get 1 head and 3 tails. And if you say, okay, well, what is, what's the probability of this exact outcome? And I'll just jot it down right here. What's the different class here? Okay, so if we say, all right, the probability of getting heads is 0.7, and the probability of tails is 0.3, then the probability of getting heads, tails, tails, tails has to be 0.7 times 0.3 times 0.3 times 0.3, okay? And that's going to be 0.7 times 0.3 cubed, okay? And if you look at any of the other ones, tails, heads, tails, tails, so if we go in this exact order, tails is 0.3, and heads is 0.7, and tails is 0.3, and the probability of tails is 0.3. And we can do the multiplication here because everything is independent of each other. Well, we're going to have 0.7. With just a rearrangement of terms, we're going to get 0.7 times 0.3 to the third as well, okay? And all 4 of these are going to have the same probability of 0.7 times 0.3 cubed. And so the total probability of each of these things, tails, 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 heads, this is also 0.7 times 0.3 cubed. This is also 0.7 times 0.3 cubed. And so the total probability, because we have 4 of them, is going to be 4 times 0.7 times 0.3 to the third. Okay. Does that kind of make sense? And so when you do that calculation, you're going to get a total of 0.0756. And that's the probability of getting exactly 1 head and 3 tails in any order. Okay, exactly 1 head and three tails in any order. Okay, and so, okay, what if we ask another question? What's the probability we get heads exactly 2 times? So we'll follow the rules of classical probability again, and this time we'll list off every possible combination to get 2 heads out of 4 flips. So if you have 4 flips and you're going to get 2 heads, then that means you have to get tails 2 times. So you need 2 heads and 2 tails. How many combinations are there? I listed them all out. Heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails, tails, heads, heads. These are all the possible sequences for getting 2 heads and 2 tails in 4 flips. And each of these, if you kind of follow the same type of thing here where you multiply out the probabilities, all of them, you're going to have 0.7 multiplied 2 times and 0.3 multiplied 2 times. So you're going to have 0.7 squared times 0.3 squared for a total probability of 0.0441 for any one of them. And you have 6 things, and they're in different orders, but they all have the same probability because you're just multiplying 0.7 and 0.7 and 0.3 and 0.3. So they all have the same probability. And so you're going to take this number, multiply it by 6, and the result is going to be 0.2646. Okay, 6 times 0.7 squared times 0.3 squared. Okay, so what we want to do is let's try to generalize this into some kind of formula. All right, so when we looked at this example where we flip it 4 times and we're looking for the probability of getting 1 head. Okay, so when we do 1 head and 4 flips, each of the sequences has 1 head and 3 tails. Okay, and we can say the probability of this is going to be 0.7 to the first times 0.3 cubed, which is equal to the probability of success raised to the number of successes multiplied by the probability of a failure raised to the number of failures. And there's 4 possible arrangements. So the total probability is the number of arrangements times this probability of success raised to the number of successes, probability of failure raised to the number of failures. Okay. And when we looked at the other example where we have 2 heads and 2 tails, it's the same thing. Number of arrangements times the probability of success raised to the number of successes, 0.7 raised to the 2nd power, times the probability of failure, which is 0.3, raised to the second power, probability of failure raised to the number of failures. And so this is pretty much the formula that we can apply in the binomial situation. The number of arrangements multiplied by the probability of success, in our case, that's 0.7, raised to the number of successes, second power, times the probability of failure, 0.3, raised to the number of failures, which is 2 in our case. Okay. So how do we figure out the number of arrangements? Okay. Well, in our examples, we were able to list off the number of arrangements, and it's not too terrible. But if you have a large number of trials, let's say you're going to do 10 trials and you want to get 5 heads, how many possible arrangements are there to get 5 heads in 10 trials? There's a lot. Okay. And so that number can be calculated using something called the binomial coefficient. Okay. And so you'd say, n choose k. This is how you read it. You got these tall parentheses where you have an n stacked on top of a k. And this just means you have n trials and you're going to have k successes. How many arrangements are there? How many ways are there to choose k successes out of n trials? And so that's going to be n factorial divided by k factorial multiplied by n minus k quantity factorial, or a factorial is basically the product of all whole numbers less than or equal to n. So 4 factorial is 4 times 3 times 2 times 1, which equals 24, and so on and so forth. Okay. So if you have 4 trials and 2 successes, you're going to have 4 factorial divided by 2 factorial times 4 minus 2, which is also 2 factorial. Okay, 4 factorial is 24, 2 factorial is 2 times 1, which is also 2. And so you do 24 divided by 4 and you get 6. Okay, something a little bit bigger, say you have 10 trials and you want to know how many arrangements are there to get 4 successes. That's going to be 10 choose 4, and you'll have 10 factorial divided by 4 factorial times 10 minus 4 quantity factorial. Okay, so this is a much bigger number, right? So 10 factorial is 10 times 9 times 8 times 7 all the way down to 1, which is 3,628,800. 4 factorial is 24, 6 factorial is 720. And when you do this computation, you get the number 210. Okay. You don't have to do the factorial business. Your calculator has an NCR button, probably. So on my calculator, this is where I would find it. Let me zoom in. So I would do 10, and then over the division button, I have an NCR. So I'm going to hit Shift, Divide, and I type in 4. So this is 10 choose 4. This is what it looks like on my calculator. 10 choose 4 is going to spit out 210. If you have a TI, you might have a math or a PRB button. So you might hit the math and then you use the arrow keys to navigate through the menu to get to the PRB section. Or you might have a PRB button for probability button directly on your calculator, and that will pop up. And you can do 10, and then you have to use the menus to find NCR, and you do 10 NCR 4. Or something like that, okay? And you would get 210. There's also on CCLE, okay? So on CCLE, if you go to week 2, I have posted reference tables. We're going to use these reference tables throughout the quarter here, or our class. And the first table is the binomial coefficients table. And you can do n, 10, choose 4. So 10 choose 4. So you have you go to the row 10 and the column J for 4, and you get 210. Okay. Now the things are is symmetric. Okay, it's symmetric. So 10 choose 4 is the same thing as 10 choose 6, right? Because like I said, how many ways are there to get 4 heads is also asking the exact same question as how many ways are there to get 6 tails, right? If you're going to flip the coin 10 times and you need 4 heads, then that means you need to get 6 tails. So the number of combinations is going to be the same. So 10 choose 4 is 210, and 10 choose 6 is 210. And you'll notice that kind of symmetry is going to exist throughout. So 14 choose 5 is 2002, and 14 choose 9 is also 2002. So you, so at a certain point, there's going to be kind of a halfway point and everything is symmetric. So the tables, I think, go up to 20 choose 10. And you don't have 20 choose 11, but it's going to be symmetric. So because 20 choose 11 is the same thing as 20 choose 9. And so anyway, these are the numbers here. Okay, so these are available in your binomial coefficients table. You have buttons on your calculator, and also in R, if you wanted to, you can choose, type it in right here, right? So you can type in choose, comma 10, comma 4. So this is how you write it, choose 10, comma 4, and you would get 210. Choose, if you have 20 flips, how many ways are there to get 10 heads? And there's a lot, 184,756. Okay. Okay. Is that okay? Any questions there? All right. So anyway, all to say that takes care of this question of how many number of arrangements are there, right? So if we put that all together, the total binomial probability is going to be n choose x, the probability of success, which is we're going to call p, raised to the number of successes x, times the probability of failure, which is 1 minus p, raised to the number of failures, which is going to be n minus x. Because if you have the total of n trials, and you're going to have x successes, right? So if we're going to have 4 trials and 2 of them are going to be heads, and that means the other 2, 4 minus 2, have to be tails. Okay. So you're going to have n choose x 0.7 squared times 0.3 squared, and that gives us our answer. R has a built-in function that calculates binomial probabilities, and that's called dbinom. So we could do it ourselves. We can do 6 times 0.7 squared times 0.3 squared. 6 times 0.7 squared times 0.3 squared, and that we get 0.2646. I can also do dbinom, and we can say I want 2 successes, 4 trials. The probability of success is 0.7, and we get 0.2646. Okay, and also the answer to this 2, 4.3. This is because we can say, what's the probability I get 2 heads out of 4 flips if the probability of getting heads is 0.7, is 0.2646. That should be the same as getting, what's the probability of getting 2 tails if I have 4 flips and the probability of a tail is 0.3. And so those 2 numbers are going to be the same, 0.2646. Okay. So question, the last slide equation is just finding the answer for the n choose k that we plug into the binomial probability. Yes, so the previous slide, this whole thing here of the binomial coefficient, this is just the answer for the number of arrangements, okay? The number of arrangements. So the number of arrangements is not the answer. Your answer is a probability. So one thing to keep in mind is if the question asks, what's the probability of this? Remember, all probabilities have to be between 0 and 1. Okay, all probabilities have to be between 0 and 1. And so, if you do your work, and sometimes it's easy to get lost in your work because there's multiple steps. And you say, oh, okay, let's do this. How many arrangements? And you do 4, 10 choose 4, and you get 210 or something. And you feel like, okay, that's it. Let's go on to the next problem. Something in your brain should say, wait a second, this can't be right. This can't be the final answer because it's a number that's bigger than 1, right? It's a number that's bigger than 1. It can't be a probability, right? And so when it says, oh, that's right, there's a whole bunch of other stuff I have to multiply by, right? I have to multiply by the probability of success and the probability of failures and stuff like that. And then your answer will be less than 1. And at least that serves as a baseline double check where it's like, if the question is, what's the probability? And you're getting an answer that's greater than 1, that can't be right. And if you're getting an answer less than 0, it also can't be right, okay? But I mean, it doesn't necessarily mean that all answers between 0 and 1 are correct, but at least if you're getting an answer greater than 1, you know it cannot be the answer to a probability, right? Okay, all right, so here's a basketball related question. So Steph Curry, one of the greatest shooters of all time, is during the 2018-2019 season. This was his shooting percentage. He was injured last year, and this year he did well. But anyway, his free throw percentage is something around 92.6%, which is, if you don't follow basketball, this is a really good free throw percentage. Okay, and so we'll just pretend that in some game he's going to take 5 free throws, and we're going to make a bunch of assumptions, which are bad assumptions here, but we're going to just set it up so we can do a binomial probability. So the question is going to be, what's the probability he misses 1 free throw? Okay, 5 free throws. He's going to take a total of 5 free throws. The probability of making a free throw is 0.926. And the probability we're asking, what's the probability he misses 1? Okay, so one thing we have to assume here is that every free throw is independent of each other. And that may or may not be a good assumption. And we also have to assume that the probability he makes a free throw is this purely random thing of, it's the same as flipping a coin or rolling a die, and that it's just that it's going to be 0.926. Okay, so in this question, the number of trials we have is n, 5, and probability of missing 1 means he's going to make 4, right? If he misses 1, that means he has to make 4 of them. Okay, so in our case, the answer is going to be found using the binomial formula, using n is 5, x is 4, and p is 0.926. The probability of making 1 is 0.926. And we're looking for the probability of making 4 out of 5. So we're going to do n choose x, which is 5 choose 4. The probability of making it is 0.926. How many times does he have to make it? He has to make it 4 times out of 5. The probability of missing, okay, is 1 minus 0.926, so 0.074. And that has to happen exactly 1 time, right? If he's going to miss 1, it has to happen exactly 1 time. And so when you do that calculation, you get something like 0.2720. Okay, and again, we can use R to calculate this. So I can do d binom, making 4 out of 5 free throws, and the probability of making it is 0.926. Okay, now, because it asks what's the probability he misses 1, you might also try using x equal to 1. Okay, you can also use x equal to 1. And if you were to do that, you would have to adjust the probability p would have to be the probability of missing, right? So we could say n equals 5. We have p equal to 0.926 and x equal to 4. And this is probability of making 4. Okay, we can also, this is equivalent to n equal to 5, x equal to 1, and what would we use for our p? Okay, what we would use for p would have to be 1 minus 0.926, and we would use 0.074. Okay, these two things are going to be exactly equal to each other. Okay, exactly equal to each other. So because the probability of making 4 out of 5 is the exact, it has to be the same as the probability of missing 1, but we have to adjust it so that p is going to be the probability of missing. So whether we're calling making it a success or missing it a success, right? And it's all a matter of perspective. You just have to be consistent in what you've labeled success and what the probability of success is. And so, whoops, just to kind of show that indeed they are equal. So d binom 4, 5.926 is going to be exactly the same as d binom 1, 5.074. Okay, and we can see that these numbers are exactly the same. Okay, all right, so why don't you guys just try one problem here? And we'll say the admission rate at a university is 16%, and we're going to say 100 people apply. And what's the probability that exactly 15 out of 100 people get admitted? Okay, and there's other questions here, but let's just, I'll give you guys a minute here and figure out your answer. Don't type your answer into the chat just yet. I'll give you guys a minute to figure this out, okay? But why don't you try this one? The admission rate at a university is 16%. 100 people apply, what's the probability we get exactly 15 admitted? Okay, I'll go ahead and pause the recording just for a moment. All right, let's just go over the answer here. Okay, so here, the probability of success, the admission rate, we're going to say is 16%. So P is 0.16, and we've got 100 people applying, and getting exactly 15 admitted will be X is 15. So we can just do D binom 15, 100, 0.16, okay? We can do 100, choose 15, 0.16. This has to be raised to the 15th power. 1 minus 0.16, which is 0.84. That has to happen to the 100 minus 15. We raise it to the 85th power. So obviously you need a calculator to compute this out, but you can also use R, and you'll get the answer. Okay, so if I punch this into R, I type in D binom 15, 100, 0.16, and we get 0.1069. I can also do choose 100, 15 times 0.16 raised to the 15th power times 0.84 raised to the 85 power. We'll get the same number there. Okay, so something around 10.7%, around 11% there. And so there's our answers, and the other questions and such are there. Okay. Okay. I think UCLA just released their admission numbers, and we're like at 10% now or something. So it's congratulations, you guys you guys got in. So it's like every year it gets harder and harder and harder to get in. Okay, let's look at this. All right, the mean of a binomial distribution. So like last week when we were looking at random variables, we said, oh, if you wanted to calculate the mean, you can take every possible outcome, multiply it by its probability, and do that and add them up for all possible outcomes. And we could do that. There's a shortcut, and we can just say the mean, the expected value for a binomial distribution is n times p. And if you think about that, this just makes logical sense, right? If you're going to try something n times and the probability of getting a success is p, your overall expected number of successes is going to be n times p, right? If you attempt something 100 times, the probability of a success being, let's say, 16% each time, with 100 trials, you'd expect around 16 successes, plus or minus a couple. But that your expectation would be n times p. Standard deviation, a little bit less intuitive, and we're not going to go into explaining it, but the standard deviation of a binomial random variable is going to be square root of n times p times 1 minus p. Okay, and that's the answer there. Okay, I totally forgot, and please remind me if I forget to give you view quiz answers and stuff. But your first view quiz answer for today, week two Monday, your first view quiz answer is the letter E. E as in elephant. E as in elephant is your first view quiz answer for today. And I will give you your second and third view quiz answers later on in the lecture. First view quiz answer is E. E as in elephant. Okay, we are going to move on and now talk about the normal distribution. So the normal distribution is a very important distribution for statistics and probability and things like that. It's also sometimes called the Gaussian distribution, also sometimes just called the bell curve. But the idea being you can put a handle on here and it would be like ringing some kind of bell, I guess. I don't know. All right. So the normal distribution is a continuous distribution. So unlike the binomial is what we call a discrete distribution because we're talking about the number of successes. And so the number of successes is going to be a whole number, right? So like when Steph Curry shoots the basketball, he's either going to make it 4 times or 5 times or 3 times or something. It's not possible for during a game that he makes 3.7 baskets or he makes 3.9 baskets. That's you can't have a fraction of a number there, okay? But for the normal distribution, it's not the number of successes, it's just some number. And that can be, it can take on decimal values, right? So we could talk about someone's height, and height might be normally distributed. And someone's height could be, we often, when you ask somebody how tall they are, they often will just round off to the nearest inch, maybe the nearest half inch. But the truth is if we had a very, very accurate measuring system, we could get a lot of decimal values, right? So someone could be 5 foot 5.2 inches. Someone else could be 5 foot 5.23 inches. Someone else could be 5 foot 5.2378 inches or something like that. If we had a very, very precise measuring device, we probably aren't so concerned about things like that. But depending on things, you could, your measurements can have decimal values, okay? And when you have something that follows the normal distribution, it is unimodal and symmetric. And what it means is that values near the middle will show up most frequently. Values that are above average and below average show up less frequently. And values that are far above average or far below average show up much less frequently, okay? So, if you think about human height, most people are of average height. You have some people who are tall, some people who are short, and then you have some people who are extremely tall, but you just don't have very many people. You also have some people who are extremely short, and you also don't have as many people there, right? Who are either extremely tall or extremely short. And so what we have is something that looks like a normal distribution where most people are kind of in the middle-ish area, somewhere between 5 and 6 feet tall, something around there. And, the farther you go above 6 foot, let's say 6'2", the farther you go above that, you have fewer and fewer people at that extremely high height. Okay, and the farther you go below, say 4'10" or something like that, you have fewer and fewer people at an extremely low height. Okay. When you take a look at this normal distribution, the total area will under the curve equals 1. Okay, so that's a key idea to remember, is that the total area under the normal distribution curve is equal to 1. Okay. So we're going to start off with the standard normal distribution. This is a picture of the standard normal distribution. The standard normal distribution is centered at 0 and has a standard deviation of 1. Okay, this is also known as the Z distribution. I don't know why it's called the Z distribution, but that's what it is. It has a mean of 0, so it's centered at 0, has a standard deviation equal to 1. Okay. This is a little bit strange to think about, but when you have a continuous distribution, the probability of getting any one exact value is 0. It's a little bit strange to think about, but if you have a continuous distribution, the probability of finding somebody with a height of exactly 5 foot 10 inches is 0. And then you go, what? That doesn't make sense. I know I'm 5 foot 10, or I know somebody who's 5 foot 10. And the truth is if we put you on the most accurate measuring device in the universe, okay, or imaginably possible, the probability that your height is going to be 5 foot 10.0000000 inches, with no deviation, right? You've got 10 and an infinite number of zeros after the decimal place and no deviation there. The probability of that happening is it's not going to happen, right? It's a probability of 0. Most likely, you could be very close to 5'10", but it's probably going to be like 5'10.01 inches or 5'9.98 inches or something. But getting exactly 10 inches with an infinite number of zeros on the most accurate measuring device possible, the probability of getting any one exact value is 0. Okay, so we always kind of define ranges. What's the probability of getting some value in some range? And that's that. Okay, so here's a question. What's the probability that we get a value less than 0, that z, the random variable, is less than 0? Okay, remember the total area under the curve is 1. The distribution is centered at 0. So what's the probability we're going to get a value less than 0? What do you guys think? Okay, well, yeah, when we draw the picture, this is what it looks like, and a lot of you guys got it right in the chat there. So here's our picture. It's centered at 0. We're drawing a line, a vertical line at 0. And basically the idea is if I shade in the area to the left of 0, how much will I have shaded? Well, the answer is going to be I've shaded in 1/2 of it, right? Because it's symmetric, it's centered at 0. I'm drawing a line right down the middle. So how much is to the left? The answer is 0.5. Okay. And so, you know, the probability that z is less than 0, we would write something like this. The probability that z is less than 0, that's going to equal 0.5. Okay. And then so the flip side is, what's the probability that z is greater than 0? Okay. Okay, what's the probability that z is greater than 0 or greater than or equal to 0? Those are equivalent, actually. Well, that's also going to be 0.5. It's the complement. The area, if the area to the left is 0.5, then that means the area to the right also has to be 0.5 because the total area is going to add up to 1. Okay. The total area is 1. Okay, I hope that makes sense. Okay, we have something called the empirical rule. This is also known as the 689599.7 rule, and the reason for this is because these are the numbers that appear. So basically, we're going to say approximately 68% of the data have z-scores between 1 and -1. Okay, that the probability of getting a z-score between 1 and -1 is something around 68%. So basically something around 2/3, okay, a little bit more than 2/3. The probability of getting something within 2 standard deviations or having z-scores between 2 and -2 is around 95% of the time. And the probability of getting something with a z-score between 3 and -3 is almost 100%. It's pretty close, 99.7%, 99.7%. Okay. Well, there's a question in the chat, and it says, is the probability that greater than or equal to, are they the same? So this is, again, for the normal distribution only, or I should say for continuous distributions only. So not the binomial. So for continuous distributions only, and the normal is continuous. The probability that, you know, z is greater than some number, we'll call it x, is equal to the probability that z is greater than or equal to that number x. Okay, and similarly, probability that z is less than x is the same as the probability that z is less than or equal to x. Okay, it's a little bit strange, but you know, so you know, what's the probability that z is less than 0? That's 0.5. What's the probability that z is less than or equal to 0? That's also 0.5. Because the probability of getting z exactly equal to 0 is 0. Okay, getting some number exactly with infinitely many zeros and after the decimal place, the probability of getting something like that exactly 0. Okay, so that was a question in the chat. Is is that? Okay, so anyway, this is the empirical rule. You get z-scores between 1 and -1 around 2/3 of the time, 68% of the time, between 2 and -2, 95% of the time, and between 3 and -3, 99.7% of the time. Let me this is kind of the diagram. Let me see if I can shade this in a little bit here. Oh dear, what's going on? So this is the idea that if we have a this is your normal distribution, the total area is equal to 1. So if I were to shade, say, well, how should I do this? Okay, we'll do green. Yes. All right, so we'll shade this in. So this area is approximately, oh goodness, what did I do? So this is around 68% between here and here, between 1 and -1. And then, kind of going on, shading out here. There and there. So if you go from there to there, that is approximately, oh, no, that's not what we want. Pen tool, please. From there to there is around 95%. Okay, and then if we go further out, hope these colors are okay. We're getting close to almost 100%. You can see there's just a tiny bit left over, right? So we go all the way out to here. You're going to get like 99.7%. Okay, almost everywhere. Okay, there's only a tiny fraction left. Okay, and this accounts for what? 0.03 or 0.3%, 0.3 of a percentage point. Okay, that's just the tiniest bit out here. Okay, and you can see, so getting values above 3, a z above 3 or a z below 3, -3 is very rare. Okay, right now we haven't defined what a z is. We just said this is the standard normal distribution. So when you have a normal distribution centered at 0 with a standard deviation of 1, most of your values are between 3 and -3. Actually, most of your values are between 1 and -1. And, certainly a lot of them are between 2 and -2. And pretty much almost everything is between 3 and -3. Almost. Okay. Very rarely do you get above 3 or below -3. Okay. But it's not impossible. And in fact, it is not impossible to get above 4. Okay. Very rare, but not impossible. Okay. And I think, you probably get like above 6. Above 6 happens, but less than like 1 in a million times. Above 6 is like less than 1 in a million. Okay. Okay. So using that, we'll define what the z-score actually is in a moment here. Using this idea here, approximately 68% have z-scores between 1 and -1. What if I ask this question? What is the proportion that has z greater than 1? What proportion has z greater than 1? What do you guys think? I ask this question. What proportion of z? What proportion has z greater than 1? So we got, okay, yeah. So we got a few people putting their answers in the chat, and yeah, that would be greater than 1. Okay, so if I've got 68% between 1 and -1, right? That means, so if we just kind of divide our picture into 3 pieces here, so we're going to say 68% between here and here, and then we've got something over here and something over here. Okay, the rest, okay, the rest has to equal basically 100% minus 68%, right? So that's going to be 32%. Okay, so I've got 32% in total on this side and this side. 32% there, which means we're going to have about 16% over here and approximately 16% on the left. Okay. Maybe my picture is no good. I should have used the oh, okay. So here is the picture here. This would have been better. Okay. So if I so we got 68% in the middle. How much is in between? How much is above 1 and -1? Okay, so we've got 68% here and here. Okay, which means this side over here and this side over here, we can say about 16% and about 16% over here for a total of, you know, everything adds up to 100%. That's kind of the idea. Okay. So we would say about 16%. Okay. All right. What if we try this? What proportion has z less than, say, 0.42? Okay. So here's a picture. All right. Here's our normal distribution. And now we want to know what proportion has z less than 0.42. So I'm not going out to 1. But I'm going to 0.42. This is kind of my picture here. And so the question is, how much is shaded here? Okay, if this is what my picture looks like, the question is, how much am I shading if I shade over here? Okay, so this we cannot answer with the knowledge that we have, right? Here, in order to do this, we know that the answer has to be more than 1/2, right? Because if I shaded everything to the left of 0, we know we would have 1/2. And here I'm shading more than that. So we know our answer has to be more than 1/2, but you know, how much? Well, we don't know. Okay, so to answer this, we have to use our reference table. Okay, so we're going to go over to our reference tables. So this is, again, on CCLE, look at reference tables. And we're going to go to the next page, okay? And you have areas under the normal curve, okay? Areas under the normal curve, it takes up 2 pages. You have the negative side and you have the positive side, okay? So here we're going to go to the positive side, okay? And our z, the z value that we're using is 0.42. Z is equal to 0.42. And the way the table works is you look up the row in the 10th place and the 100th place is in the column. So we're going to go to the row is 0.4 and the column will be 0.02. Okay. So here so when you look up z is equal to 0.00, you see the area to the left is 0.5. Okay. And as you go a little bit higher, you get more and more. So here I'm going to go z is the row 0.4 and the column 0.02. Okay, are you guys able to see this? Row is 0.4, column 0.02. And so the answer here is 0.6628. 0.6628 is my answer. Okay. 0.6628. Okay, so I go to the row 0.4 and the column 0.2. Okay, so here we go to the z, the row is 0.4, the column 0.02, 0.02, 0.6628 is our answer. Okay. You can also look up the answer using R. and there's a function called p norm for give me the probability in the normal distribution. And you type in basically z equal to 0.42. And it gives you also 0.6628. It gives you more decimals of precision. So the it's not exactly 0.6628, it's 0.66275, but if we were to round to 4 decimal places, it would round to 0.6628. So that's what we have there. Is that all right? Okay, so it's important to always remember that when you use the table, it's always going to give you the area to the left, always the area to the left. If you ever want the area to the right, okay, so if we ever want this side, okay, so here the answer is what's the probability that z is less than 0.42? That answer is 0.6628. If we ever ask what's the probability that z is greater than 0.42? The answer to this is going to be what? It's going to be 1 minus 0.6628. Okay, because the area to the left is 0.6628, and we know that the two sides have to add up to 1. Okay, so if I have 0.6628 on the left, then on the right, I'm going to have 1 minus 0.6628. Oh, that's not what I want to do. Undo. 1 minus 0.6628, 0.3372. 0.3372. And that way everything adds up to 1. Okay, so if you ever want the area to the right, you have to subtract the value that comes from the table from 1. And we would do that. 1 minus 0.6628 is 0.3372. Okay. We feel okay about this? All right. So then here's a few exercises. I want you guys to try using your normal distribution table, or you can use you can use R as well. Okay, you can use R as well, but use your reference table and answer these 3 questions, and pay attention to whether we are asking for the area to the left using the less than sign or the area to the right when you see the greater than sign. So what's the probability that z is less than -1.4, -1.04, or greater than 1.04? Okay. All right, so I'm going to go ahead and pause here, and we'll resume in just a minute here. Okay. Okay, so let's go ahead and take a look at our answers. And I think you guys, so the first one, what's the probability that z is less than -1.4? We'll go to our table. We go to the we'll go to the row -1.4 and the column 0, 0, and I get 0.0808, right? And then we say, what's the probability that z is less than -1.04? -1.04. So I go to again, the row is 1.0 and the column is the 0.04 column. So row -1.0, the column 0.04, which is that one, I get 0.1492. Okay. And then we ask, what's the probability that z is greater than 1.04? Okay. Well, what I'll do here is I'm going to write 1.04, and the area to the left, it will come from the table. The area to the left is 1.0. We go to the column 0.04. And okay, and the area to the left is 0.8508. Okay, 1.0, the column 0.04, 0.8508. But the question is asking the greater than sign. So we want this side. We're going to do 1 minus 0.8508. And we also get 0.1492. Okay. All right. It's good, I hope. All right. And so those last two questions I chose with the intention. All right. Oh, and if you used R, you would get the same values, except just with more decimals of precision. So 0.080756, which will round off to 0.0808 at 4 decimal places. 0.14917, which would round off to 0.1492 with 4 decimal places. Okay. And I have this slide that just says, the reason why I picked this one is for these two, the area to the left of negative 1.04 was 0.1492, and the area to the right of positive 1.04 is also 0.1492. Okay, and if you think about it, the normal distribution is symmetric. So if you think, okay, what's the area to the left of negative 1.42? Negative 1.04. If you flip that around over a mirror, you would get, oh, okay, the area to the right of positive 1.04 would be exactly the same, right? So because they're mirror images of each other. And so, so technically, you only really need the left side of the table, right? You only need 1/2 of the table, and you could use, mirrors to get the other side. But, for convenience, they give you both the negative and positive side of the table. But so the area to the left of Z, or the area to the right of Z, is equal to the area to the left of negative Z. All right, so this is kind of a picture. The area to the left of negative 1.04 is equal to the area to the right of positive 1.04. Okay, so the area to the left of Z is equal, or area to the right of Z is equal to the area to the left of negative Z. Okay. So that's a useful shortcut. If that makes sense to you and you're comfortable with using the shortcut, you can use the shortcut. If you're not comfortable with the shortcut, you don't have to, okay? Just find the area. Just remember, the table always gives you the area to the left. And if you want the area to the right, you subtract it from 1. Okay, that will always work as well. All right, let me go ahead and give you your second view quiz answer. Today's second view quiz answer is C. C as in cat. C as in cat is your second view quiz answer. Okay, so what we can do is, so far we've been working with the standard normal distribution. And what we'd like to do is we'd like to generalize this. So we have the general normal distribution. And one amazing thing about the normal distribution is that all normal distributions have the same exact shape. And they're really just rescalings of the standard normal distribution. And what I mean by a rescaling is, it's basically, you're just kind of taking that standard normal distribution shape and you're just sliding it up and down the number line, and you're kind of just stretching it wider or compressing it thinner. Okay. And so, so we could talk about heights of adult men in the United States. So, self-identified men in the United States will, we can survey their heights and we can say, all right, we can say, this is approximately normal. It's not going to be exactly this, all right? And these are, I've rounded off numbers, and so it's not exactly this, but just for simplicity, let's say the mean is 69.5 inches, okay? So around 5'9.5" is going to be around the mean. And then we're going to say we have a standard deviation of 3 inches, standard deviation of 3 inches. Okay, so we're going to ask what proportion of adult men in the United States are shorter than 72 inches. So that's 6 feet tall. Okay, what proportion of heights are less than 72? Okay, and so this is kind of our picture here. I'll go ahead and zoom in. Oops. Get this capture. Struggles. Okay, so we've got So this is kind of our picture. We've got this mean is 69.5, and the height that we're looking at is 72. And we want to know, what is this area over here? What's the area? What proportion of heights are below 72 inches? Okay, so we want to know, what is this area? Okay, so what we're going to do, okay. Oh, so this is a shorthand way. All right, so you can say the normal distribution. To say something follows a normal distribution, you can say height, and you use the tilde or the squiggle. You can say normal distribution 69.5, comma 3, right? And this means the mean is 69.5 and the standard deviation is 3, okay? Mean and standard deviation. So this is just kind of a shortcut of saying that the mean is 69.5 and the standard deviation is 3, okay? So what proportion are shorter than 72? What we first need to do is we need to convert to a z-score. We need to convert this height 72 into a z-score. Now, a z-score, I didn't write the definition, but a z-score is basically our distance from the mean okay, but expressed in standard deviations. Right? So if you are 1 standard deviation above the mean, your z-score is 1. If you are 2 standard deviations above the mean, your z-score is 2. So here we say, okay, well, how far above the mean are we, right? So if the mean is 69.5 and we are at 72, we can do, okay, our distance from the mean is going to be 72 minus 69.5. We are 2.5 inches above the mean, okay? But we can say, how many standard deviations is that? So we're going to divide that by 3. The size of each standard deviation is 3. And so our z-score is, we are not quite 1 whole standard deviation above the mean. If we are 1 whole standard deviation above the mean, that would take us to 72.5. We're not quite there. We are 2.5 out of 3. We are 0.833 standard deviations above the mean. Okay, so the z-score is basically distance from the mean divided by size of the standard deviation. Okay, or we would just do x minus the mean, that's the distance from the mean, divided by sigma, the size of your standard deviation. This is the z-score formula. This is how you calculate a z-score. It's your distance from the mean expressed in standard deviations. Okay, and so we are 2.5 inches above the mean. Each standard deviation is 3 inches. So we're not quite 1 standard deviation above the mean. We are 0.833 standard deviations above the mean. Okay, does that kind of make sense there? Okay, so here we write, so the probability that height is less than 72 is equivalent to saying what's the probability that z is less than 0.83. Okay, so if you round off to 2 places, your z-score is 0.83. And so at that point, we would go to the z table, and we're going to find z is equal to 0.8. The column is 0.03, and we find the answer is 0.7967. And 0.7967. So the probability that z is less than 0.83, we'll just round off 0.7967. So this is from the table, the z table. This is what we get. Okay, so once the question in the chat, can I reiterate what 1 standard deviation above the mean would be for this example? Okay, so our mean is 69.5. 1 standard deviation, each standard deviation is 3. So 69.5 plus 3 would be 72.5. This would be 1 standard deviation above the mean. So that would take us to 72.5. If I go 1 standard deviation below the mean, That would be what, 66.5? This is 1 SD below the mean. All right, is that okay? So you find the z-score, which is your distance from the mean, but expressed in standard deviation. So 1 standard deviation above would be 72.5 inches, and we're not quite there. We're at 72. So our z-score is a little bit less than 1, 0.833. Okay, if we feel okay with that, let me give you this example. All right, what proportion of adult men in the US are shorter than 71 inches? What proportion of adult men in the US are shorter than 71 inches? So why don't you guys try this one out? And again, I'll pause the video. And if you're following along in the video, because you didn't attend live, that's fine. I would recommend that you also pause the video and you try this example out. Okay, so go ahead and take a minute here and try out this example. Okay, and then again, when you get your answer, give me a thumbs up. Okay, so we'll go over our answer. It looks like some of you guys got your answer, and some of you guys might still be working on it, and maybe some of you are just waiting for me to do do it for you, and that's fine. But I do think if you try it out yourself, it's always better. All right, so this is kind of my picture. We're at 69.5 is the center, and this time we are drawing a line at 71, right? And we want to know, okay, how much are we shading over here, right? So this is, how much are we shading? What is this area? So we want to find the z-score, which is basically our distance from the mean in standard deviations, right? And so we're going to say z is equal to whatever our value is minus the mean divided by our standard deviation. So we are at 71. We subtract off the mean of 69.5. Each standard deviation is 3 inches. So we are 1/2 of a standard deviation above the mean. Okay, 1/2 of a standard deviation above the mean. So we're going to ask, what's the probability that z is less than 0.5? What's the area that z is less than 0.5? So we go to our table, we go to 0.5. We don't, this is 0.50, okay? So we go to our table, 0.50, 0.6915. So the area, the probability that z is less than 0.5 is 0.6915. This is my answer, 0.6915. Okay, what proportion are shorter than 71 inches? We go through it, we get our z-score. We go to our height, we get 0.6915. Okay, 71 inches there. Okay, so here is the next example. Okay, what is the probability that a randomly chosen adult male has a height between 71 and 72 inches? A height between 71 and 72 inches. Okay, so the question, this is a struggle to draw, but here we've got 69.5. We've got 71 here, and we have 72 here. And the question, and actually let me okay. And the question is, what is this area right here? Okay, what is the probability that somebody has a height between 71 and 72? Okay, this is our question. We want to know, what's the probability that somebody has a height between 71 and 72 inches? Okay, so the answer, the way we're going to find this, okay, is we're going to take, oh, that's not what we want to do. Okay, we're going to do that there. And then do this, okay? All right, so the answer is equal to area to the left of 72 minus area to the left of 71. Okay, so does that make sense? We're going to get this answer, we're going to take the area to the left of 72 and we're going to subtract the area to the left of 71. So if you take the area to the left of 72 and you subtract off the area to the left of 71, the piece that you'll be left over with is going to be the area between 71 and 72. Okay, all right, and so from the previous slide, okay, the area to the left of 72 is back here, 0.7967. So this area is 0.7967. And over here, the area to the left of 71 is 0.6915. I wrote the wrong letters here. It should say height rather than Z. I apologize. This is a typo. Slide 42 typo. Maybe I got to fix that. Okay, but anyway, so we've got 0.7967. This is the probability that height is less than 72, and this is equal to the probability that height is less than 71. Okay, I should just abbreviate this height. So we're taking the area to the left of 72, subtracting off the area to the left of 71, okay? And so this area is going to be 0.7967 minus 0.6915, and we get 0.100, wait, no, 1052, 1052, okay. No, 105, did I can't do my math, right? 1052, okay, good. All right. Does that make sense? Are there any questions there? So to get the area in between two areas, you find the area to the left of the one, and then you find the area to the left of the other, and you take the difference between them. Okay, so the area to the left of 72 minus the area to the left of 71. Okay. So that's your diagram there. This is kind of picture. What's that area? That's this area minus this area. Okay. All right. Let me go ahead and give you your third view quiz answer, the last view quiz answer. Please don't just leave after you get your last view quiz answer. Last view quiz answer is the letter D. D as in dog. D as in dog is the last view quiz answer. All right, and so this is also very important. We want to be able to work backwards, okay? So sometimes you're given like a percentile or some number, and you want to figure out what's the corresponding value that works with that thing, okay? So so let's say you are a hat manufacturer, okay? And you want to like make sure your hat is adjustable and it can fit like people with big heads, and you know, you can also adjust it so that people with smaller heads and stuff can also fit, okay? I have no idea. I made up these numbers, so don't get mad at me if these numbers aren't true, okay? So we're gonna say we want our hat, you know, it's gonna be one size fits most, okay? We want our hat to fit 96% of people's heads, okay? So if people with the, you know, 2% of the biggest heads won't fit and the 2% of the smallest heads won't fit, but it'll fit most people, okay? So we're gonna say max size will be the 98th percentile, and the smallest size we need to fit will be the 2nd percentile. And this will kind of cover the middle 96% of people, okay? And so again, just making up some numbers, okay? We're gonna say the mean head circumference is 23 inches and the standard deviation of head circumference is 0.8 inches. Again, don't quote me on this. I just made up these numbers and I picked nice round numbers for easy work here, okay? All right, so what we wanna do is basically, the question is, what is this number? What is the number that corresponds to here, okay? We're going for the middle 96%. And here we really just, let's just focus on the 98th percentile, okay? Okay, so we'll let's work on this. So we're gonna work backwards. We're given the area, okay, and we want to know what is this number, okay? And what we know is that the area to the left is equal to 0.98, okay? So this is what we do know. We know that this area, if I shade over here and here, this area to the left is 0.98, okay? And so the question is, what is the height? What is the height? Or not height, what is the head circumference? Okay. So we're gonna say head size comes from a normal distribution. The mean is 23 and the standard deviation is 0.8. Okay. So first of all, first question is what Z corresponds to an area .98. Okay. What Z corresponds to an area of 0.98. Okay, so the area here is equal to 0.9800. Okay, 0.9800. So the important thing here, when we work backwards, is do not look up Z equal to 0.98. Do not look up Z, do not use Z equal to 0.98. This is wrong, okay? Don't do that, okay? What we want to do is we want to go through the Z table, and there's a lot of numbers, but they're in order. We want to find the Z that corresponds to the area closest to 0.98, okay? And so we have two values that are really close. We have 0.9798 and we have 0.9803, 0.9798 and 0.9803, okay? 0.9798 corresponds to 2.05 and 0.9803 corresponds to 2.06, okay? 2.05 or 2.06, all right? And so between the two, I would say 0.9798 is just a tiny bit closer to 0.98 than to 0.9803, okay? So if we're looking at the value closest to 0.98, we would probably pick 2.05. Probably the value that corresponds to 0.98 would be something in between, like 2.055, but don't worry about like trying to interpolate or anything like that. So we'll just do 2.05. We'll say Z equal to 2.05 corresponds to area 0.9798, which is very close to 0.9800, right? So we want something as close as possible to the 98th percentile, and kind of the value that we have that's very close, we're going to use Z equal to 2.05. 2.05. I want to make sure we're okay with that. Finding the Z score that corresponds to a certain area. Okay, so then the question is, okay, what head size will give me a z-score of 2.05, okay? Gives z-score of 2.05, okay? Well, here we can just use the z formula. Z is x minus the mean divided by the standard deviation. We plug in the values we know. And so we know that z is 2.05. We don't know what this x is. We know that the mean is 23. And we know that the standard deviation is 0.8. Okay, so we have 2.05 is equal to x minus 23 divided by 0.8. And now we just use algebra to solve for x. So we're going to do 2.05 times 0.8 is equal to x minus 23. We add x to both sides. And so now I get 23 plus 2.05 times 0.8. And what is that? That's going to be 23 plus 2.05 times 0.8. 24.64. Okay, and so this answer, so having a hat that goes up to 24.64 inches will correspond to the 98th percentile of head circumference. And there's our answer. Okay, so what is the 98th percentile? All right, so the z-score, first we got to find the z-score that gives 0.98 to the left, all right? And we do that. The z-score that gives 0.98 to the left is 2.05. And we solve backwards from there. And we get 24.64. Okay, so it's in the slides. I hope that makes sense. Okay, so one more exercise for you guys. And this time we're going to ask, find the head circumference that corresponds to the third percentile. I know in my example I said we want the second to the 98th percentile, but the second percentile would be trivial just because it's like the mirror image of the example we just did. So this time, find the head circumference that corresponds to the third percentile. Try working on that. Okay, so you got to kind of go through the table, find the z that gives you an area of 0.03, and you work from there. Okay. Again, if you're watching the video, I'm going to pause the video here, and I recommend that you pause it as well. And we'll go over the answer in just a moment. Okay, so let's just go over the answer here. What head circumference corresponds to the third percentile? So this time, our diagram is just kind of like the opposite side. Okay. So we've got 23 in the middle here. We've got some height here, and we just know that this area is equal to 0.03. So what, and again, normal distribution, mean 23, standard deviation 0.8. So what area, or what z-score gives me an area of 0.03, okay? So the z that we're going to use, we're going to go to our table. This time we go to the negative side, and we're going to look for the z that gives me something close to 3%, okay? And we've got a bunch of numbers, okay? But here, this number right here is pretty close to exactly 3%. It's 0.0301, okay? We've got 0.0307, 0.0294. 0.0301 is really close, and that's a z-score of negative 1.88. Negative 1.88 gives me a area of 0.0301, okay? Negative 1.88. So z equal to negative 1.88, right? And so now we'll just use the z-score formula to figure out what the corresponding x is. So I'm going to plug in negative 1.88 is equal to the unknown x minus the mean of 23 divided by the standard deviation, 0.8. So I've got 23 minus 1.88 times 0.8. And our answer, 23 minus 1.8 times 0.8, get an answer of 21.496. Okay, so this is going to be head size 21.496 is our answer. Okay, now a common mistake, or not a common mistake, is just, I think sometimes students will make a decimal mistake. So sometimes students will look up 0.003, okay, instead of 0.03. So they'll look up like the height, the value that corresponds to 0.003 and use like negative 2.75. And that will just give you the wrong answer. Okay, so just make sure you, when you go from a percentile to a thing, you use the correct answer. So you use 0.03, negative 1.88, not negative 2.75 or something like that. Okay. I hope we're good there. I hope we're good. Okay. All right. The last bit here is the normal approximation to the binomial distribution. I've got just a few minutes to go over this. And the idea here is when you have a large sample, when you have a very large sample, the binomial distribution can be approximated with the normal distribution. And this applies only when the sample size is large. And what that means is that n times p is greater than or equal to 10, and the quantity n times 1 minus p is greater than or equal to 10. So if you have p equal to 0.5, n equal to 20 is large enough. So n times 20 times 0.5 is 10, and 20 times 1 minus 0.5 is also 10. That's going to be big enough. But if you say have a p of 1%, 0.01, then your n has to be really big. You need an n of, say, 1,000. N of 1,000 will give you 1,000 times 0.01 will give you 10. And 1,000 times 1 minus 0.199 will give you, 990, which is greater than 10. But you would need a much bigger p. So if p is something like 0.1 or 0.99, you need a much bigger n. Whereas if you have p equal to 0.5, you can have an n as small as 20. Okay. But anyway, when that's the case, when you have a large sample, the binomial distribution can be approximated with the normal distribution. Okay. And the normal distribution that will approximate it will be the mean. We'll have mean NP and standard deviation square root of n times p times 1 minus p. And if you recall, these are the same numbers that came, way back on this slide back here. Okay, where the mean is NP and the standard deviation is NP times 1 minus p. These are the same values there. Okay. All right. So why would we want to do this? Okay. We would want to do this because sometimes the true answer can become very tedious. So for example, we could ask a question, I will flip a fair coin 100 times, and what's the probability that it will land 6 heads 65 times or more? So the true answer to this will require us to do something like n is 100, x is 65, x is 66, x is 67, x is 68, because it says 65 times or more, and we would have to go x is 9 all the way up through x is 99, x is 100. There would be like 36 values for us to calculate. Each of those would be n choose x times p to the x times 1 minus p to the n minus x. It's a lot of work, okay? We can approximate it using the normal distribution. The unfortunate thing, or not unfortunate thing, is that the normal distribution is continuous. The binomial distribution is discrete. So there's a thing we have to do known as the continuity correction to apply, all right? I've got it all written in these slides here, but I think maybe a couple examples will just help. Will make a little bit more sense, okay? So our example, we're going to start with this example that says we're going to flip a fair coin 100 times. So n is 100. The coin is fair, so p is 0.5, and we want to do probability that x is 65 or more. So that means x is 65, 66, 67, all the way up to 98, 99, 100, okay? We don't actually want to compute all of these things. So the normal approximation as mean equal to NP and standard deviation equal to the square root of N times P times 1 minus P. Okay, so if I plug these in, 100 times 0.5, we're going to have mu equal to 50 and standard deviation equal to the square root of 100 times P, 0.5 times 1 minus 0.5, which is 0.5. We're going to get the square root of 25. Sigma is going to equal 25. So where the mean is 50 and the standard deviation, oops, is 5. Okay, so we're going to have we can approximate this with a normal distribution with a mean of 50 and standard deviation of 5. Okay, so we're going to start there. And then what we need to do is basically, this is kind of our normal distribution. It's centered at 50, and we're going to go out to 65, and we want everything higher than 65, 65, 66, 67, so on and so forth, all the way up to 100. You could imagine having a bar centered at 65, a bar centered at 66, a bar centered at 67, so on and so forth. I'm going to zoom in here, okay? We're going to zoom in into this portion on the next slide here, okay? Because what we want is we want everything 65 and higher. Okay, so imagine having a bar centered at 65. We'll have a bar centered at 66. We'll have a bar centered at 67. We'll also have a bar centered at 64 and a bar centered at 63. So on and so forth. Okay, you got more and more bars. All right, and what we want the area. So remember, the question, keep in mind the question, what is the probability it lands heads 65 times or more? $65 times or more. So the answer to our question will require us to shade in the bar for 65, the bar for 66, the bar for 67, whoops, and everything higher, okay? Okay, so on and so forth. So notice when I shade in the bar at 65, okay, if I were to draw a cutoff line at 65, I would only be getting half the bar, right? If we draw a cutoff line at 65, we only get half the bar. All right, and I apologize for going a couple minutes over here. Okay, so what we want to do is we want to draw the cutoff line between 64 and 65. So the cutoff is at 64.5 rather than 65. We're not drawing it at 65, we're drawing it at 64.5. Okay, and at this point it becomes just a regular standard normal problem with cutoff at 64.5, mean is 50, standard deviation is 5. We get a z-score of 2.9, and then we shade everything to the right. Okay, so if you do this, you get 64.5 minus 50 over 5. Your z-score is 2.9, and the probability of being greater than 2.9 is 0.0019. Okay, and that's our answer there. Okay, if the question was something like, what is the probability it lands heads more than 65 times? Okay, and in that case, all right, what is the probability it lands heads, say, more than 65 times? Okay, more than 65 times would mean we only want the bar at 66 and higher. Okay, so we would actually not want this one, right? And so our cutoff line would be at 65.5. Does that make sense? So it depends on how the question is written. So here it says 65 times or more. 65 times or more means we want the bar centered at 65. We want this bar. What is the probability it lands heads more than 65 times? We don't want the bar centered at 65. We would draw the cutoff line at 65.5. Okay. So there's a difference. And so the wording of the question makes a difference, right? Because 65 times or more is a different question than more than 65. Okay. That is it. Thank you for your patience and willing to stick around for a few extra minutes, but we will end here for today's lecture. And so have a good night, and we will see you guys on Wednesday. And I'll also stick around for office hours if you have questions. Okay.